So TON is a complicated system, and nothing could be even more complicated in TON than its model of transaction costs and fees. So let's take a deep dive into what kind of fees exist in TON. But first of all, let's talk about why this is important. So TON is a public network, and like any public network, it is subject to attacks by anyone who wishes to do so. And so extra care should be taken of protecting this shared resource from denial of service attacks. And this means that if there is any non-trivial cost that some participants in the network bear that could be amplified by the external actors, this creates a huge risk for the liveliness of the whole ecosystem. And that's why anything that has any noticeable cost and can be amplified must be accounted for explicitly in terms of fees. Now, in TON, there are generally three categories of fees. This is the gas cost, the rent, and the message fees. Let's talk about each of them in detail. And what are the gas fees? TON is a computation platform. Your contract may contain arbitrary code, and anyone can upload into the network any code they want. So once they do that, then the whole network will process messages running this code. And so this code could contain loops, it could create extra large amounts of data, and all of this should be accounted for in terms of some payment so that everyone who bears this cost get in return transaction fees and deter attackers from exploiting their resources. The term gas comes from the gasoline, like a fuel for the execution, and it was originally invented in Ethereum. The idea is that for each operation in your code, there is a nominal gas cost that allows you to specify how some operations are more or less expensive than the others. And then there is a global parameter that specifies the gas price, that specifies how much all of these gas units cost at the present prices. And the idea is that the price of the TON coin could vary from time to time, and therefore the gas price should be adjusted to reflect the real costs of execution. So for instance, if TON coin is increased in price 10 times, then you probably want to adjust the gas price down by a factor of 10 to not make the computation more prohibitively expensive. And TON is designed, unlike Ethereum or Bitcoin, in a way that doesn't produce the market for the scarce amount of gas or the block size. Instead, it shards infinitely, so that if you pay one gas price today and tomorrow you have much higher load, then the validators of the network will earn higher fees, but the users will not have to compete on fees and will pay the same price, just the network will scale out horizontally. Now, mechanically, what happens in the TVM, when the code is executed, every instruction is checked for correctness, and then your balance is reduced by the cost of the gas that this instruction incurred. And by the end of the execution, if your balance didn't run out of money, then execution is completed successfully. But if you do run out of balance due to gas costs, then the execution aborts in the middle, and all the gas payments are collected, meaning that your new balance will be recorded as such, but the new storage for the contract will not be applied. And you as a designer have to take care of a couple of considerations regarding gas. You should take care of deciding who is going to pay for the gas costs, whether it's your contract or it's the sender of a message that sends the message to this contract. And more often than not, the best strategy is to put all the costs on the sender and design your contract in a way that the costs are more or less predictable to the senders, so they could attach enough coins to their message to cover the gas costs. And then the code of the contract will just limit the gas usage to this amount that they received. And if they ran out of this amount, then the contract will not change its state, and it's just the sender of the message will lose their money on fruitless computation. Sometimes you want to, for convenience or for whatever other reasons, decide that you will increase the gas limit and let the contract pay for itself. But then you have to take extra care of verifying that the message came from the trusted source that will not exploit this ability. So sometimes you may, decide that this is an unauthenticated message, but you will do a couple of checks, make sure that your gas cost will be limited. Now to the second category of costs, which is rent. So rent is simply defined as a cost of a single bit of data that the contract stores per unit of time, which is a second. So it's really defined in a very granular manner, per bit and per second. But it's not charged on a basis of each second. Instead, we know that the contract does not change its state in between transactions. So what happens instead, nothing happens to a contract in between transactions. And then when a new transaction begins, this is where a storage phase that we talked about previously kicks in, where we take all of the amount of time that the contract existed since the previous transaction and multiply this by the size of the storage occupied by the contract. And then we compute the amount of, what I mean by the whole network computes the amount of rent that the contract owes to the network for this amount of time and charges it from the balance of the contract. And you may notice if you use a wallet that if you haven't used the wallet for several days, then the first transaction that you send has a slightly higher fee than the next one. This is because your wallet was idle for a week or two and some noticeable amount of rent accumulated that was charged when you did this transaction. And then next transaction happens maybe a minute later and has negligible amount of rent. And so you will see the difference in fees that may seem random, but it's actually the rent that was charged for all the idle time of the contract. And finally, the third category is a number of fees for importing and creating outgoing messages. And there are various fees that are charged per message, per byte, with various prices. And also this applies to the update of the storage of the contract. So this comes to play in the action phase when your contract creates the outgoing messages and specifies new state for itself. And these are typically quite low fees because there's not much data transmitted between the contracts. But this is a third category that you as a contract designer should take care of. So let's talk about a couple of pitfalls and considerations in the design of smart contracts around gas and rent payments. So first of all, you obviously don't want your contract to run out of gas limit in the ordinary valid transactions, and you don't want your contract to run out of rent because then it will be frozen and get stuck until it's refilled with coins. So how to make sure that your contract exists? First of all, anyone in the network can send TON coins to any contract to refill their balance. And so if you have a decentralized app that has a shared user base and is not having any particular operator, then any user could make this contract live further by just topping up its balance. And sometimes in the logic of your contract, you can encode a portion of the funds that are transferred in the messages to refill its own balance. Secondly, if you put the cost of the gas and execution on the sender, then you may not always be able to guarantee some specific cost of execution for various reasons, but what you could guarantee is some kind of upper bound. So this means that the sender would attach some amount of coins that exceeds the necessary amount charged by the network for the gas, and the rest of the coins would otherwise be deployed and deposited on the contract's balance. So to make it more usable, there's a pattern in design of the contracts where the contracts send excess coins as a reply message to the address that the sender specifies. So it could be back to the sender or to some other wallet. So for instance, if you are transferring tokens, the token transfer is operated through additional messages, and you have to attach some amount of TON coins to this message to make sure to cover the gas costs. And you typically want to put a little bit more just to make sure that it succeeds. But then there will be a separate additional message that sends all the unused amount of coins back to your wallet. This is a pattern that people design in the systems on TON to make sure that the users attach enough coins to avoid failures, but at the same time don't overpay unnecessarily for the fees. And finally, one more consideration is regarding bounded execution of the contracts. Strive to design your contracts to be of a constant cost in terms of storage and in terms of computation, because this way your rent and your gas costs could be more predictable. If you have a variable length data structure that grows, for instance, with every transaction, then the costs of operating in this contract are not predictable neither to your users nor to the contract author. And this makes it very easy to slip into mistakes where contract runs out of money and may even enter inconsistent state. So the best way to avoid these situations and avoid the complexity of dealing with it is to design your contracts to be of a limited size and limited cost of execution.